In December 1944, a U.S. Navy Gato-class fleet submarine suffered catastrophic flooding in her forward torpedo room while transiting Norwegian waters, forcing an emergency surface in a fjord controlled by German naval forces. Within hours, the USS Barb SS-220 was in German hands, her crew captured, her secrets exposed to an enemy desperate to understand why American submarines were achieving operational successes that German U-boats could only dream of achieving. 4. Kriegsmarine. Submarine commanders who had spent years perfecting the art of undersea warfare in vessels that creaked and groaned at depths beyond 300 feet, who had learned through bitter experience that diving below safe limits meant crushing death in milliseconds. The Barb represented a revelation that would force them to confront an uncomfortable truth, that American industrial philosophy had built submarines capable of routinely operating at depths where German U-boats dare not venture, that the 412-foot test depth printed on captured technical manuals was not bravado but conservative engineering, and that this depth advantage provided tactical options in combat and evasion that explained why American submarines survived and thrived while U-boats died in increasing numbers. This is the story of how experienced submarine commanders learned that depth capability was not merely a technical specification, but a survival characteristic that determined whether crews lived or died when hunted, and how their honest reports documented Germany's inability to match American submarine engineering despite pioneering the technology decades earlier. Subscribe now for the untold stories of World War II's undersea war, where battles in the depths were decided not by who had braver crews or better tactics, but by who built submarines that could dive deeper, stay down longer, and survive the crushing pressure that turned steel hulls into coffins. We're bringing you the claustrophobic reality of submarine warfare that other channels never capture. Hit subscribe. It's December 18th, 1944. Trondheim, Norway. The morning is brutally cold, winter gripping the Norwegian coast with temperatures well below freezing. Snow falling steadily from a gray sky that seems to touch the mountains surrounding Trondheim Fjord. Kaptein Zersi Werner Hartenstein stands on the dock at the German naval base, hands thrust deep in the pockets of his heavy wool coat, studying the submarine moored before him with an expression that mixes professional interest and something closer to dread. The USS Barb sits low in the water, her dark gray hull streaked with rust and ice, her conning tower bearing damage from depth charging, but otherwise intact, floating calmly in enemy waters 3,000 miles from her home port of Pearl Harbor. The submarine was captured 4 days ago after catastrophic flooding in the forward torpedo room, forced an emergency surface in Trondheim Fjord. The flooding, caused by a combination of battle damage and equipment failure, left the submarine unable to dive or maneuver effectively underwater. The American crew, 80 men total, surrendered rather than risk destruction in a vessel that could not submerge. They are now prisoners of war held at a Wehrmacht facility outside Trondheim. Their submarine belongs to Germany now, a prize of war and intelligence windfall. And for Hartenstein, a deeply troubling education in just how far German U-boat technology has fallen behind American submarine development. Hartenstein is 38 years old, one of the Kriegsmarine's most experienced submarine commanders with 2 years commanding U-156, a Type IXC U-boat, before being promoted to staff duties overseeing submarine operations in Norwegian waters. He has sailed over 100,000 miles underwater, has sunk 20 Allied merchant ships totaling 97,000 tons, has survived 14 depth charge attacks that left his U-boat limping back to port with hull plates cracked and systems failing, and understands submarine warfare as well as any man alive. He has also, unlike many in the Kriegsmarine leadership, paid careful attention to intelligence reports describing American submarines encountered by German forces in various theaters. The reports describe vessels substantially larger than U-boats, with longer range, heavier armament, and operational capabilities that exceed German boats in almost every category except perhaps diving depth, where German boats were thought to have advantage due to their smaller size and robust construction. Hartenstein initially believed this assumption, but recent intelligence from interrogated American submariners and captured technical documents has suggested something disturbing, that American fleet submarines can dive significantly deeper than the 280-foot test depth of the Type VIIC U-boat or the 330-foot test depth of the Type IXC, and that this depth advantage provides tactical flexibility in combat that German commanders can barely imagine. The Barb is enormous compared to U-boats Hartenstein knows intimately. The hull is 311 feet long, 27 feet in beam, displacing 1,525 tons surfaced, 2,424 tons submerged. A Type IXC U-boat, Germany's long-range submarine, is 252 feet long, 20 feet in beam, displacing 1,144 tons submerged. The barb is 40% longer, 35% wider, displaces more than double the tonnage. Size itself is not necessarily an advantage. Larger vessels are slower to dive, easier to detect, require more resources to build. But size enables capabilities impossible in smaller vessels. Greater fuel capacity allowing longer patrols. More provisions supporting larger crews for extended periods. Additional torpedo storage enabling sustained operations. Redundant systems providing reliability. And most significantly, stronger hull construction supporting deeper diving. The question Hartenstein needs to answer, the question that keeps him awake at night, is whether the Americans have actually built submarines capable of routinely diving to depths that would crush a U-boat, or whether the reported depth capabilities are exaggerated propaganda meant to intimidate German submariners. He suspects with growing certainty that the capabilities are real, and that realization is professionally terrifying. Behind Hartenstein, 3 other officers wait in the December cold. All experienced submariners selected for their expertise and their ability to evaluate honestly without letting propaganda or wishful thinking cloud their judgment. Corvetting-caping Heinrich Lehmann-Willenbruck, 33 years old, one of Germany's most successful U-boat commanders with 25 ships sunk totaling 183,000 tons. Holder of the Knight's Cross with oak leaves. Recently reassigned from combat operations after his boat U-96 was lost in a bombing raid. Captain-Lieutenant Reinhard Hartigan, 33 years old, a former commander of U-123. Famous for devastatingly successful operations off the American East Coast in early 1942 when American coastal defenses were virtually non-existent. Now serving in training command after medical issues ended his seagoing career. And Oberleutnant zur See Hans-Joachim Schwank, 28 years old, an engineering officer specializing in submarine pressure hull design and construction. Assigned from the Submarine Construction Office in Kiel specifically to evaluate the barb's structural capabilities. These 4 men collectively represent over 200 war patrols, thousands of hours submerged, hundreds of depth charge attacks survived, and systematic understanding of what submarines can and cannot do in combat. They are here to answer one question that matters more than any other. Can this American submarine really dive to 400 feet safely? And if so, what does that capability mean for the underwater war? Before boarding the barb, the 4 officers interview the captured American commanding officer, Commander Eugene Fluckey, 33 years old, from Washington, D.C., who has commanded the barb since April 1944 and accumulated one of the most aggressive combat records in the U.S. submarine force. The interview occurs in a room at the Naval Headquarters Building, a requisitioned Norwegian government office overlooking the harbor. Fluckey sits on one side of a wooden table, the 4 German officers opposite. A translator present, though Fluckey speaks adequate German learned during pre-war exchange programs. Fluckey is cooperative within the bounds of the Geneva Convention. He will discuss technical details of his submarine, which Germany now possesses and can examine freely, but will not discuss tactics, patrol areas, or strategic information. Hartenstein asks about diving depth. Fluckey explains matter-of-factly that the Gadio class has a test depth of 412 feet, meaning the depth to which the submarine can dive routinely and safely during normal operations. The collapse depth, the theoretical depth at which hull failure occurs, is estimated at 600 to 700 feet based on engineering calculations and safety factors, though no captain would intentionally approach that limit. In practice, Fluckey says, he has taken the barb to 450 feet during emergency evasion when pursued by Japanese destroyers, and the hull showed no signs of distress, no concerning creaks or groans beyond normal pressure sounds, no leaks beyond routine seepage through hull penetrations. The submarine was designed with substantial safety margins specifically to allow deep diving during combat when pursued by enemy forces. Hartenstein listens with mounting disbelief. 412 feet test depth. 450 feet operationally tested without distress. 600 feet estimated collapse depth. The Type IXC U-boat has test depth of 330 feet. Collapse depth estimated at 500 feet, based on pre-war testing that pushed hulls to destruction. The difference is 82 feet of additional safe operating depth, nearly 25% deeper. This is not marginal advantage. This is categorical superiority in one of submarine warfare's most critical characteristics. Depth determines survival. When depth charged by enemy destroyers, when pursued by enemy escorts, when caught in shallow waters with nowhere to hide, the ability to go deep means the difference between life and death. A submarine that can dive to 450 feet can position itself below the depth where most depth charges are set to explode, can use thermal layers at depths where pursuing ships lose sonar contact, can exploit deep water channels and underwater terrain features that shallower diving submarines cannot access. The tactical advantages compound geometrically. Hartenstein asks how often the barb dives below 300 feet. Flucky responds that during combat patrols in enemy waters, the submarine routinely operates at 300 to 350 feet when evading, dives to 400 feet or deeper when heavily pursued, considers depths below 300 feet as normal combat operating environment rather than emergency measure. The casualness with which Flucky describes diving to depths that would terrify German submariners is perhaps the most disturbing aspect of the conversation. Hartenstein asks about crew reactions to deep diving. Flucky says that American submarine crews are trained extensively in deep diving procedures during workup before deployment, that every submarine conducts deep diving exercises to test depth as part of sea trials and periodic maintenance cycles, that the crews become accustomed to the sounds and sensations of deep submergence, and that confidence in the boat's structural integrity comes from knowing the engineering margins and seeing the submarine routinely perform as designed. German U-boat crews, Hartenstein knows, are taught to fear depths beyond test limits, are trained to stay well above maximum safe depth except in extreme emergencies, hear constant warnings about the dangers of diving too deep. The cultural difference reflects engineering confidence or lack thereof. American crews trust their boats to handle deep diving because the boats are designed, built, and tested to handle deep diving. German crews fear deep diving because their boats are built to lighter standards with smaller safety margins, and depth beyond limits often means death. Hartenstein asks about structural damage from deep diving. Flucky responds that the Barb has conducted 11 war patrols, has dived deep dozens of times during combat, and has experienced no structural damage attributable to diving depth. Only normal wear from pressure cycling and routine maintenance items like packing gland replacement and valve seat refurbishment. The hull integrity is maintained through regular inspection and preventive maintenance, but the basic structure shows no degradation from deep operations. The interview ends. Flucky is returned to the POW facility. Hartenstein and his team are left with notes, specifications, captured technical manuals, and the submarine herself for detailed evaluation. They board the Barb through the forward torpedo room hatch, descending a vertical ladder into the submarine's interior. The contrast with U-boats is immediately apparent even before diving. The interior is spacious, clean, well lit by electric lighting that seems bright compared to the dim illumination in U-boats. The forward torpedo room houses 6 torpedo tubes arranged in 2 rows. 3 tubes per row, with 16 torpedoes and storage racks filling the available space. The torpedoes are Mark 14s, 20 feet long, 21 inches in diameter, carrying 643-pound warheads. German torpedoes are comparable in performance, but German submarines carry fewer. The Barb carries 24 torpedoes total, 14 in the forward room, 10 in the after room, enabling extended operations without rearming. The torpedo reload equipment is sophisticated, with hydraulic hoists and power assist mechanisms that reduce reload time significantly compared to the manual handling required in U-boats, where torpedo loading is an exhausting process requiring multiple crew working for 30 minutes per torpedo. Moving aft from the forward torpedo room, they pass through crew berthing areas. The bunks are arranged in stacks of 3, each bunk with a mattress, sheets, blankets, reading light, and privacy curtain. The spaces are clean, painted white. Temperature comfortable despite the freezing conditions outside due to heating systems that work efficiently. Lamin Willenbruck, who has lived in U-boats for years, comments quietly that these berthing spaces are more comfortable than the officers' quarters on a Type VIIC. Each crew member has a personal locker for belongings, a luxury German submarines cannot provide due to space constraints. The passageways are wide enough for men to pass each other without squeezing against bulkheads or equipment, with overhead clearance sufficient to stand upright without ducking, except in a few locations. Type VIIC passageways require constant ducking, constant awareness of protruding valves and pipes, constant risk of head injuries. The Barb's interior layout prioritizes crew comfort and operational efficiency, accepting weight and space penalties for better habitability and easier maintenance access. The control room is located amidships, directly below the conning tower. It is spacious, approximately 20 feet long by 15 feet wide, with multiple control stations arranged logically for efficient operations. The diving station controls ballast and trim systems. The helm station controls course and speed. The radar and sonar station integrates detection equipment. The chart table provides navigation workspace. 2 periscope wells allow raising periscopes for redundancy and different viewing purposes. Everything is well organized, clearly labeled in English, which the German officers can mostly read. Ergonomically arranged for operators who will spend hours at their stations during submerged operations. German control rooms are more cramped, with stations positioned wherever they fit structurally rather than where operators would ideally want them. The American design philosophy prioritizes operational efficiency even if it requires additional space and weight, betting that effective operations produce better outcomes than weight optimization. The engineering spaces aft contain the diesel engines and electric motors driving the propellers. The 4 Fairbanks Morse diesels are massive, each displacing 38 liters and producing 1,600 horsepower, totaling 6,400 horsepower available for surface propulsion and battery charging. Type IXC boats have 2-man diesels totaling 4,400 horsepower. The power advantage allows the Barb to cruise at higher speeds on the surface, maintain speed against worse sea conditions, and charge batteries faster. The American engines are also quieter, better insulated with sound dampening mounts and acoustic shielding. U-boat diesels are notoriously loud, making extended surface running in hostile waters dangerous due to acoustic detection risk. The Barb's electric motors, 2 General Electric units totaling 2,740 horsepower, provide underwater propulsion. Type IXC electric motors total 1,000 horsepower. The power advantage gives American submarines better underwater speed and maneuverability, critical for positioning during attacks and evasion during depth charging. But what Schwank examines most carefully is the pressure hull itself, the structural element that determines diving depth and survivability. He documents hull plate thickness throughout the submarine using ultrasonic measuring equipment brought from Kiel, specifically for this purpose. The pressure hull plates vary from 7/8 inch thickness in the least stress sections to 1 1/8 inch in the most stress sections around the control room and engine room. By comparison, Type IXC pressure hull plates are 5/8 inch to 7/8 inch. The American hull is significantly thicker, providing greater strength against external pressure. The hull steel itself is high tensile strength alloy, yielding at approximately 50,000 pounds per square inch compared to German submarine steel yielding at approximately 42,000 pounds per square inch. Stronger steel allows thinner construction for equivalent strength or thicker construction for greater strength. The Americans chose thicker construction with stronger steel, prioritizing depth capability over weight optimization. Schwank examines the hull frame spacing, discovering that the Barb's frames are spaced more closely than German practice, approximately 16 inches on center compared to 20 to 24 inches in Type 9 boats. Closer frame spacing provides more support to pressure hull plates, distributing loads more evenly, preventing local buckling under pressure. He examines the welding quality, running his hands over seams, looking for irregularities or weak points. The welding is exceptional, consistent, showing none of the variability that characterizes late war. German submarine construction where quality control has degraded due to labor shortages and production pressure. American submarine construction, he realizes, benefits from factory conditions that Germany lost years ago. The submarines are built in dedicated facilities by skilled workers using consistent materials and proven processes. Quality is maintained through systematic inspection and testing. Every weld is radiographed to detect internal flaws. Every hull penetration is pressure tested. Every system is validated before the submarine goes to sea. The result is structural integrity that can be trusted at depths where German boats would fail, not because of design limits but because of construction quality issues. Schwank documents his findings meticulously, knowing that his superiors will need detailed evidence to believe that American submarines are really this much better. December 20th, 1944. The Kriegsmarine authorizes a test dive of the Barb, to be conducted by a mixed crew of German submariners and Norwegian naval personnel who have basic submarine experience. The test will be carefully controlled, progressive, starting shallow and going deeper incrementally while monitoring for any signs of hull stress or system failure. The goal is to verify the reported test depth of 412 feet, or at minimum to dive significantly deeper than German U-boats can safely operate, proving that the American depth advantage is real rather than propaganda. Extensive testing is risky. The submarine is in enemy hands with a crew unfamiliar with her systems, operating in Norwegian waters where Allied forces could attack at any moment. But the intelligence value justifies the risk. If American submarines can routinely dive to depths where German U-boats cannot follow, then every tactical assumption about submarine warfare needs revision, and the Kriegsmarine needs to understand the magnitude of the disadvantage. Hartenstein will command the test dive with Lehmann Weilenbroek as executive officer, Schwank as engineering officer monitoring hull integrity, and a crew of 30 German submariners supplemented by 20 Norwegian naval personnel performing basic duties under close supervision. Preparation takes 2 days. The Barb systems are checked thoroughly, every valve verified in correct position, every pump tested for proper operation, every control system confirmed functional. The Germans study the captured operating manuals intensively, learning startup procedures, trim calculations, emergency protocols. American submarine operations are more complex than German U-boat operations due to additional systems and greater automation, but the fundamental principles are identical. Both submarine services share the same basic physics and engineering. On December 22nd, at 0800 hours, The Barb's diesel engines rumble to life, the exhaust burbling into the cold morning air. Hartenstein is in the conning tower, Lehman Weilenbroek in the control room. Schwank positioned near the depth gauges where he can monitor for any signs of unusual hull behavior. Lines are cast off. The Barb moves away from the dock under her own power, heading down Trondheim Fjord toward deeper water suitable for diving tests. The handling characteristics on the surface are immediately apparent to Hartenstein, who has commanded U-boats in all weather conditions and knows how submarines should feel. The Barb responds smoothly to helm orders, turning gradually with wide radius due to her size, accelerating slowly but steadily to 15 knots cruising speed. The ride is stable, the hull slicing through light seas without excessive pitching or rolling. The bridge is spacious, with good visibility and effective windscreens protecting the watchstanders from wind and spray. U-boats have cramped bridges exposed to weather, with minimal protection for personnel who must endure brutal conditions during winter operations. The American submarine prioritizes bridge crew comfort, recognizing that cold, wet, exhausted lookouts make mistakes that cost lives. After 2 hours of surface running to reach suitable water depth, Hartenstein orders preparations for diving. The test will be conducted in a fjord area where water depth exceeds 700 feet, providing adequate safety margin for even the deepest planned test depths, while remaining within controlled waters where rescue is possible if something goes catastrophically wrong. At 0930 hours, Hartenstein orders dive. The diving klaxon sounds throughout the submarine, a loud alarm that brings all hands to diving stations. Crew members who are smoking or resting or performing routine maintenance drop everything and move to assigned positions with practiced efficiency. The Germans have been drilled on diving procedures for 2 days, but this is the first actual dive, and tension is palpable. Everyone understands that they are diving an enemy submarine whose systems they barely understand. With a crew that has never worked together in frigid waters where any flooding could be fatal, hatches are sealed. Vents are opened, allowing air to escape from ballast tanks. The Bar begins settling into the water, the buoyant lift decreasing as tanks flood, the submarine becoming heavier. The transition from floating ship to submerged vessel occurring smoothly. The bowplanes tilt downward, controlled by plainsmen following orders from Lehman Willenbrock, who is managing the dive based on procedures learned from captured manuals and advice from interrogated American submariners. The Barb submerges smoothly, taking approximately 60 seconds from diving alarm to fully submerged at 60 feet depth. Type VIIC U-boats can crash dive in 20 to 30 seconds, a critical advantage when surprised on the surface by aircraft. The Barb's slower dive reflects her larger size and different operational doctrine. American submarines typically operate in areas where they have warning of aircraft approach through radar or visual sighting, allowing time for orderly dives. Boats operate in heavily patrolled waters where seconds matter, where the difference between 30-second dive and 60-second dive is the difference between survival and destruction. Different operational environments produce different design priorities. Once submerged, the first sensation Hartenstein notes is the quietness. The Barb is remarkably quiet underwater, the electric motors barely audible, the hull generating minimal noise, equipment operating with smooth mechanical precision. U-boats are noisier underwater with more mechanical sounds, more water flow noise over hull imperfections, easier to detect by enemy sonar. The Barb's acoustic quieting reflects American emphasis on stealth, recognizing that quiet submarines survive longer in hostile waters. Hartenstein orders the submarine to level at 100 feet while trim is adjusted and systems are verified. At 100 feet, approximately 30 meters, the Barb floats neutrally stable with minimal control input required. The depth gauge is read precisely 100 feet in the control room, confirmed by pressure gauges showing external pressure of approximately 44 pounds per square inch. Everything is normal. The hull is silent except for routine sounds of equipment operation and water flow outside. Crew members begin to relax slightly, the initial tension of the first dive easing as the submarine performs as expected. Hartenstein orders descent to 150 feet. The plainsman angles the bowplanes downward. The Barb descends smoothly at a controlled rate of 30 feet per minute, gentle enough to monitor systems and halt descent immediately if problems develop. At 150 feet, the submarine levels again. Hull pressure is now approximately 66 pounds per square inch. Still normal, still quiet. Schwank listens carefully for any unusual sounds, any creaking of hull plates under increasing pressure, any groaning of frames or buckling of structure. He hears nothing concerning. The hull is solid. Hartenstein orders descent to 200 feet. The same procedure, controlled descent, leveling at target depth, waiting to verify everything is normal before proceeding deeper. At 200 feet, approximately 60 meters, they are approaching the depths where German submariners become nervous. Type VIIC test depth is 280 feet, but prudent commanders stay well below that limit except in emergencies. At 200 feet in a Type VIIC, you hear the hull. You hear plates flexing under pressure. You hear rivets creaking. You hear water seeping through stuffing boxes and cable penetrations. The sounds are normal, expected, but they remind you constantly that the ocean is trying to crush you and only thin steel stands between life and death. At 200 feet in the barb, the hull is still quiet. No creaking, no groaning. Schwank notes in his log that hull sounds are minimal, indistinguishable from sounds at 100 feet. The American hull is stronger, stiffer, showing less flex under pressure that would cause audible sounds in German boats. Hartenstein orders descent to 250 feet. This depth is deeper than Type VIIC's safe operating depth of 220 feet, the practical limit where German commanders stop diving unless absolutely necessary. At 250 feet in a Type VIIC, you are gambling with your crew's lives, hoping the hull holds, knowing that any weakness could mean explosive compression and instant death for all hands. At 250 feet in the barb, the submarine continues to feel solid. There is some noise now, subtle sounds of pressure on the hull, but nothing alarming, nothing that suggests stress approaching dangerous levels. Schwank examines visible hull plates in the control room and engine room, looking for any signs of deformation or buckling. He sees nothing. The plates are flat, unstressed, showing no visible deflection. He touches the hull, feeling for temperature changes that might indicate stress concentrations. The metal is cold, uniform, showing no hot spots. The hull is handling the pressure load as elite. Hartenstein orders descent to 300 feet. They are now at approximately 90 meters, the depth where Type IXC submarines approach their test depth of 330 feet. At 300 feet in a Type IXC, you hear the boat complaining. The hull flexes measurably. Pressure hull plates between frames show slight inward bowing. Seepage through hull penetrations increases. Crew members become very quiet, moving carefully, speaking in whispers as if loud sounds might disturb the delicate equilibrium keeping the hull intact. At 300 feet in the barb, the hull begins to make sounds. Not alarming creaks, but subtle groans as steel compresses under 130 pounds per square inch external pressure. Schwank notes the sounds, comparing them to sounds he has heard in German submarines at lesser depths. The barb's hull sounds at 300 feet are comparable to Type IXC sounds at 250 feet. The American hull is handling 33% more pressure with equivalent stress levels. This confirms the engineering analysis. Thicker plates, stronger steel, closer frame spacing, all combining to create a pressure hull significantly more capable than German designs. Laman Willenbruck, standing at the diving station watching trim carefully, says quietly that in U-96 at this depth, the hull would be groaning constantly. That water would be dripping from multiple penetrations requiring crew to continuously pump bilges. That he would be preparing to surface quickly if depth charge attack occurred, because going deeper would risk hull failure. In the barb at 300 feet, the systems show no distress. Bilge levels are minimal. Pumps operate normally without excessive load. The submarine feels solid, safe, deep, but not dangerously so. Hartenstein makes a decision. They will continue to 400 feet, the reported American test depth, the depth that American crews consider routine. But they will go slowly, monitoring carefully, ready to halt or reverse at first sign of trouble. He orders descent to 350 feet. The plainsman angles the bowplanes downward. The barb descends. At 350 feet, 107 meters, they are now deeper than any German U-boat dives except in extreme emergencies. Deeper than Type IXC test depth of 330 feet, in the regime where German submarines experience hull failure if construction has any weaknesses. The pressure is 152 pounds per square inch, over 10 atmospheres, pressing inward on every square inch of hull surface with crushing force. The barb's hull responds with increased sounds, clear groaning now, the sound of steel under significant stress, but still nothing that suggests imminent failure or dangerous deflection. Schwank examines visible structure carefully. He sees slight inward bowing of pressure hull plates between frames, visible deflection of perhaps 1/4 inch, exactly what structural calculations predict for this pressure level. The deflection is elastic within design limits, producing no permanent deformation. The frames show no buckling. The welds show no cracking. The hull is performing exactly as designed, handling pressure that would destroy a U-boat with controlled, predictable structural response. Hartenstein asks Schwank for assessment. Schwank responds that structural behavior is normal for this depth, that observed deflections match engineering predictions, that there is no indication of approaching structural failure, that continuing to 400 feet appears safe. Hartenstein orders descent to 400 feet. The final 50 feet of descent feel interminable despite taking only 90 seconds. Every man in the submarine is silent, listening, waiting, wondering whether the American engineers who designed this hull really understood the forces involved or whether 400 feet will be where the hull finally gives up. At 380 feet, Schwank hears a sharp crack. a metallic sound that freezes everyone. He traces the sound to its source, a pressure gauge backing plate flexing, not hull structure. He announces this immediately, preventing panic. At 390 feet, another sound. Louder groaning from forward but identifiable as ballast tank pressure equalization, not hull stress. At 400 feet, they level off. The depth gauges read precisely 400 feet. The pressure gauges show 174 pounds per square inch external pressure, 122 meters depth. The USS Barb floats at her test depth, the depth to which American crews dive routinely. The depth that American engineers certified is safe for unlimited operations. The hull sounds are pronounced at 400 feet, constant groaning as steel compresses, but not the screaming that would indicate approaching failure. Schwank examines the structure one final time. The pressure hull plates show inward deflection of approximately 3/8 inch between frames, more than at 350 feet but still well within elastic limits. The frames remain straight. The welds remain intact. The hull penetrations show minimal seepage, just slight dampness around cable and pipe penetrations, nothing requiring pump intervention. The submarine is handling 400 feet exactly as designed. Hartenstein holds the depth for 5 minutes, allowing everyone to experience this depth, to understand viscerally what American submarines do routinely, to recognize that the tactical environment they thought they understood is actually dramatically different. At 400 feet, the Barb is invisible to surface ships whose sonar cannot penetrate the thermal layers and stick water density gradients at this depth. At 400 feet, depth charges set for typical depths of 150 to 250 feet explode harmlessly far above. At 400 feet, underwater terrain features like channels and seamounts that are inaccessible to shallower diving submarines become tactical advantages. The depth advantage is not merely technical. It is operational supremacy in the underwater domain. Hartenstein orders ascent to periscope depth. The Barb rises smoothly, the pressure decreasing. The hull sounds diminishing, the submarine climbing through the water column at controlled rate. At 100 feet, the hull is silent again, the brief excursion to 400 feet, leaving no detectable damage or permanent deformation. At 60 feet, periscope depth, Hartenstein raises the periscope and scans the horizon, verifying no threats are present. The fjord is clear. The test dive is complete. He orders surface. The Barb blows ballast tanks, compressed air forcing water out, buoyancy increasing, the submarine rising toward the surface like a breaching whale. She breaks through with a surge of white water cascading off her deck, floating heavily as ballast tanks drain. The conning tower appearing above the waterline. The bridge clearing enough for Hartenstein to climb up and breathe fresh air after 3 hours submerged. The test dive to 400 feet was successful, proving beyond any doubt that American submarines possess depth capabilities German U-boats cannot match. Back at Trondheim, Hartenstein immediately begins compiling observations for the formal evaluation report. The 4 officers meet in a commandeered office building 3 kilometers from the naval base, the same building where Hartenstein interviewed Flucky days earlier. They gather around a large table covered with notes, diagrams, pressure calculations, and photographs of the Barb's structure. The conversation is subdued, professional, but marked by uncomfortable recognition that they have just proven German submarine technology is inferior in a fundamental way. Hartenstein writes the operational assessment, comparing American fleet submarine capabilities against Type 7 and Type 9 U-boats across the specific dimension of diving depth. The data is stark and sobering. Test depth comparison. GTO class 412 feet. Type VIIC 280 feet. Type ESK 330 feet. American advantage, 82 to 132 feet deeper safe operations. Collapse depth estimates. GTO class 600 to 700 feet. Type VIIC approximately 500 feet. Type IXC approximately 660 feet. American advantage, 0 to 200 feet additional emergency depth. Operational depth capability. GATO class routinely operates 300 to 450 feet during combat. Type VIIC rarely exceeds 250 feet. Type IXC rarely exceeds 300 feet. American advantage, 150 to 200 feet deeper routine operations. The numerical advantage translates to categorical tactical superiority. American submarines can dive below effective depth charge range, can use deep thermal layers for sonar concealment, can exploit underwater terrain inaccessible to shallower boats, can evade pursuit by going deep in situations where German boats must stay shallow and face destruction. Hartenstein's analysis continues with brutal honesty about what this depth advantage means for submarine warfare. When depth charged by enemy destroyers, American submarines have options, German submarines do not. They can dive to 400 feet, below the typical depth charge settings of 200 to 250 feet used by most escort vessels. At 400 feet, even depth charges that detonate relatively close produce reduced damage due to pressure differential and water absorption of blast effects. German submarines, unable to dive so deep, must endure depth charge attacks at depths where the weapons are most effective. When pursued by enemy escorts with active sonar, American submarines can dive through thermal layers that occur at depths between 250 and 350 feet in many ocean areas. These thermal layers reflect or refract sonar beams, creating zones where submarines become difficult or impossible to detect. German submarines, unable to reach these depths, cannot exploit thermal layer protection and remain detectable throughout evasion attempts. When operating in areas with complex underwater topography, channels, valleys, seamounts, American submarines can use terrain at depths where German submarines cannot operate. A 400-foot deep channel allows an American submarine to transit concealed while German submarines must stay shallower and remain exposed. The depth advantage compounds in unexpected ways, Hartenstein writes. American submarine crews train extensively at deep depths, becoming comfortable with deep operations, developing confidence in their boats. This confidence allows aggressive tactics, rapid deep dives when threatened, willingness to remain deep for extended periods during evasion. German crews, trained to fear depths beyond test limits, are psychologically constrained even when tactical situations might justify deeper diving. The American crews trust their boats. German crews fear their boats will fail if pushed too hard. This psychological difference, rooted in engineering capability difference, produces operational tempo difference that favors Americans. Hartenstein notes that during the test dive at 400 feet, he felt safer than he has felt in U-156 at 250 feet. The barb's hull felt solid, stable, designed for this depth. U-156 at 250 feet felt fragile, stressed at the edge of safe operations. The difference is not courage or crew skill. The difference is engineering and construction quality. Lehman Weilenbrook contributes assessment from the perspective of a combat commander with extensive depth charge evasion experience. He describes multiple occasions where U-96 was pursued by British corvettes and destroyers, where depth charges rained down for hours, where the submarine was forced to dive as deep as possible, hoping to escape destruction. In every case, U-96's depth was limited to approximately 300 feet maximum due to structural limits. At 300 feet, depth charges set for 250 feet still caused significant damage. Hull plates buckled, rivets loosened, leaks developed requiring constant pumping. In the barb at 400 feet, depth charges set for typical depths would explode 150 feet above the submarine, far enough that damage would be minimal unless the weapon detonated almost directly above. Lehman Willenbrook writes that if U-96 had been capable of diving to 450 feet during several specific attacks, the boat would have survived easily, where instead she suffered damage requiring weeks of repair. The depth advantage is survival advantage, measured in boats that return to port versus boats that disappear forever. Hartigan contributes perspective on how depth capability affects offensive operations, not just defensive evasion. American submarines attacking enemy ships have tactical flexibility German submarines lack. They can approach targets from greater depths, using depth for concealment during approach, surfacing only briefly for periscope observations, diving deep immediately after torpedo attacks. German submarines attacking convoys typically operate at periscope depth, 60 to 80 feet, throughout attacks because diving deeper significantly slows the boat and limits situational awareness. Remaining at shallow depth makes the submarine vulnerable to counterattack by escorts. American submarines can dive to 300 feet immediately after launching torpedoes, evading counterattack before escorts can respond effectively. The depth capability enables hit-and-run tactics that German boats cannot execute. Hartigan notes that during his successful attacks off the American East Coast in early 1942, he operated almost entirely at periscope depth because diving deeper meant losing contact with targets and giving up attack opportunities. If he had possessed barb's depth capability, he could have conducted attacks more aggressively, taken greater risks, achieved more sinkings with less danger to his crew. Schwank contributes detailed engineering analysis of why the barb can dive deeper than German submarines. His assessment technical but accessible to operational commanders who need to understand the problem. The primary advantage is pressure hull construction, he writes. American submarines use thicker pressure hull plates, up to 1 1/8 inch in critical areas compared to 7/8 inch maximum in German boats. The steel is higher strength, yielding at approximately 50,000 psi compared to 42,000 psi in German submarine steel. The frames are spaced more closely, providing better support to pressure hull plates. The welding quality is superior, consistent throughout the hull with no weak points. The combination produces a pressure hull approximately 30% stronger than Type IXC hulls and 40% stronger than Type VIIC hulls, directly translating to 30 to 40% greater safe operating depth. Schwank notes that German submarine designers knew how to build deeper diving submarines. The engineering principles are not secret. Thicker plates, stronger steel, closer frames, better welding, all produce stronger hulls. But implementing these principles requires resources Germany lacks in 1944. Thicker plates require more steel per submarine, reducing production numbers. Higher strength steel requires better manufacturing processes and quality materials increasingly scarce under Allied bombing. Closer frame spacing increases manufacturing time and complexity. Better welding requires skilled workers and quality control that German submarine construction yards lost as war progressed and skilled workers were drafted or killed. American submarine construction occurs in dedicated facilities with stable workforces, consistent materials, and systematic quality control. German submarine construction in 1944 is dispersed, desperate, rushed, using inferior materials and unskilled labor under constant bombing threat. The result is boats that meet minimum standards but lack the engineering margins that enable reliable deep diving. Schwank's conclusion is depressing. Germany could design deeper diving submarines but cannot build them in current circumstances with available resources. The report, 68 pages including technical appendices, is dated December 24, 1944, classified Geheim Kommandosach, top secret command matter, and forwarded to Großadmiral Karl Dönitz, Commander-in-Chief of the Kriegsmarine and former commander of the U-boat force. It reaches Dönitz's headquarters on December 27th. Dönitz reads it over 2 days, his expression darkening as he processes the implications. He has commanded U-boats, understands submarine warfare intimately, recognizes that depth capability is not minor technical detail but fundamental operational characteristic. On December 29th, he convenes meeting with senior staff to discuss the findings and possible responses. The meeting occurs at U-boat headquarters in Berlin, in a building scarred by bombing, windows covered with blast protection, walls showing cracks from near-miss bombs. 12 officers attend, representing operational commands, technical departments, construction oversight. Dönitz opens by reading selected passages from the report aloud, his voice flat, emotionless. When he finishes, silence fills the room for long seconds. Then the objections begin. Konteradmiral Eberhard Gott, chief of U-boat operations, argues that depth advantage is less important than the report suggests, that U-boats have achieved tremendous success despite depth limitations, that tactical skill and crew determination matter more than technical specifications. Dönitz cuts him off sharply. The report is accurate, he says, based on actual diving tests in the captured submarine, confirmed by interrogation of American submariners, supported by engineering analysis. The Americans can dive 130 feet deeper than Type VIIC boats, 80 feet deeper than Type IXC boats. This advantage is real and significant. God persists. German U-boats have different missions, different operational environments. Depth is less critical in Atlantic operations than in Pacific, where Americans face Japanese anti-submarine forces. Dönitz responds, Allied anti-submarine capabilities have improved dramatically. Depth charge tactics have evolved. Escorts now use variable depth settings precisely because they know submarines dive deep when attacked. American depth advantage allows their submarines to exploit these tactical developments, while German boats remain vulnerable. Another officer, Kapitän Zersi Heinrich Lehmann Willenbruck, a different person from the officer who evaluated the barb, argues that Germany should immediately begin construction of deeper diving U-boats incorporating lessons from the barb evaluation. Dönitz acknowledges this as correct recommendation but notes the practical impossibility. Redesigning U-boats for greater depth requires thicker pressure hull plates, stronger frames, better welding. This increases steel requirements per boat by 20 to 30%, reduces production rates by similar amounts. Germany is already struggling to maintain U-boat construction rates under Allied bombing. Diverting additional steel and manufacturing capacity to build deeper diving boats means building fewer boats overall. Fewer boats means reduced operational presence, reduced sinkings, reduced strategic impact. The choice is between building more boats with current limitations or fewer boats with better depth capability. In late 1944, with the war clearly approaching its end, there is no time to implement design changes, establish new construction standards, and produce enough improved boats to affect the war's outcome. The discussion continues, circling the same insoluble problem. The barb evaluation proves American submarine superiority in depth capability. German submariners understand the tactical implications, but Germany cannot respond effectively because the required changes demand resources. time, and stable industrial conditions that no longer exist. Dunetz ends the meeting by ordering the report distributed to submarine training facilities, combat flotillas, and construction offices as lessons learned documentation, but no operational changes are mandated. Germany will continue operating existing U-boats with existing limitations because no alternative exists. He writes a personal letter to Hartenstein acknowledging the report's accuracy and thanking him for honest assessment, but noting that strategic reality sometimes requires continuing operations even when tactical conditions are unfavorable. The letter is dated December 30th, 1944. It is the last official communication Hartenstein receives regarding the Barb evaluation. He understands its meaning. The assessment changed nothing because nothing can be changed. The captured Barb remains at Trondheim through January and February 1945, used for training German submariners in American submarine capabilities, teaching lookouts how to identify fleet submarines, briefing commanders on American tactics based on captured documents and interrogated crew. In March 1945, as Allied forces advance and Norway's strategic situation deteriorates, orders come to destroy the Barb to prevent recapture. On March 14th, demolition charges are placed throughout the submarine's interior, in the torpedo rooms, control room, engine rooms, detonated in sequence that sinks the Barb in Trondheim Fjord. The wreck remains there, a tomb for technology Germany captured, evaluated, understood, but could never replicate in time to matter. The knowledge existed. The capability to act on the knowledge did not. Post-war, the submarine evaluators scatter. Hartenstein survives, surrenders to British forces in May 1945, spends 2 years in POW camps, is released in 1947, returns to Germany, works in shipping industry, retires in 1965, dies in 1978. In a 1970 interview, he reflects on the Barb evaluation with mixture of professional interest and deep regret. The experience of diving to 400 feet in an American submarine, he says, was revelation in understanding how far German submarine technology had fallen behind Allied development. The Barb felt safe at 400 feet, he says, safer than U-156 felt at 250 feet. That difference, that engineering gap, represented industrial and technical superiority Germany could not overcome. Laman Willenbruch survives, becomes one of Germany's most decorated submariners. Works in post-war maritime industry. Dies in 1993. In a 1985 memoir, he writes extensively about the Barb evaluation and its implications. So the American submarine, he writes, was not just deeper diving but fundamentally different in design philosophy. American engineers built for survival, accepting weight penalties to ensure crew safety. German engineers built for efficiency, minimizing weight to maximize performance. American approach produced submarines that brought crews home. German approach produced submarines that achieved tactical success but often died in the attempt. Hartigan survives, becomes successful businessman, lives until 2007. In a 1998 interview at age 85, he reflects on how depth capability affected submarine warfare. The Americans, he says, understood that submarine survival was more important than any other performance characteristic. A submarine that cannot dive deep enough to escape depth charges is a submarine that will eventually be sunk. The Barb could dive deep, stay deep, operate effectively at depths where German boats could not survive. This capability, this survival characteristic, explains why American submarine losses were so much lower than German U-boat losses, despite both forces operating in hostile waters against determined enemies. The depth advantage was life advantage. Schwank survives, works in post-war German submarine construction, contributes to development of Type 205 and Type 206 submarines for West German Bundesmarine, dies in 1991. In a 1975 technical paper on submarine structural design, he uses the Barb evaluation as case study in how construction quality and engineering margins determine operational capability. Modern submarines, he writes, incorporate lessons from the Barb: thicker pressure holes, closer frame spacing, higher strength materials, quality control emphasis, all producing boats that can dive deeper and safer than earlier generations. The Barb demonstrated these principles in 1944. Post-war submarine design universally adopted them. The real USS Barb survived the war with one of the most successful combat records of any American submarine: 12 war patrols, 17 ships sunk totaling over 96,000 tons, numerous additional ships damaged. The only submarine to sink a train via landing party that placed explosives on coastal railroad tracks. Recipient of Presidential Unit Citation. Her commanding officer Eugene Fluckey awarded Medal of Honor for extraordinary heroism during multiple daring attacks. The Barb was decommissioned in 1954, sold for scrap in 1972. Her legacy is preserved in museums, memorials, and in the memory of successful submarine operations, proving that deep diving capability was survival capability. The broader lesson of the submarine evaluation is that depth capability in submarine warfare is analogous to altitude capability in air warfare. The side that can operate in unreachable regimes has decisive advantage. American submarines could dive to depths where German U-boats could not follow, could hide at depths where enemy sonar could not detect, could evade at depths where depth charges were ineffective. This advantage, combined with better sonar, radar, torpedoes, and operational doctrine, produced dramatically lower loss rates for American submarines compared to U-boats. The German officers who dived the Barb to 400 feet understood this immediately. Their superiors understood eventually, but understanding came too late to develop responses. Knowledge without capability to act on knowledge is merely another form of defeat. The Barb evaluation revealed that depth capability was survival capability in submarine warfare, that engineering margins determined whether crews lived or died when hunted, and that American industrial philosophy prioritizing robustness over weight. Optimization produced submarines that could dive deeper and safer than German boats despite Germany pioneering submarine technology. The German submariners understood this after diving to 400 feet, but understanding without resources to respond is just recognition of defeat. If you want more stories about how engineering philosophy and industrial capabilities shaped World War II's undersea war, subscribe now. We bring you these untold stories every week. Thanks for watching.